Hello beasties, and welcome back to Once Upon a Lecture. I hope you are prepared for the most challenging lecture of the entire course, led by none other than Maleficent. The topic of today's lecture is the One Way ANOVA. Let's take a look at some of the topics we'll be talking about. The first thing we need to clarify is, what is an ANOVA? Well, ANOVA stands for Analysis of Variance, but we really need to understand what that means. So after a brief introduction on the analysis of variance, we will revisit the topics of between subjects and repeated measures. This should sound familiar from my friend the Wicked Witch's lecture that you attended last week. Then we're going to talk about the different types of variance that we analyze with an ANOVA. So the first thing we need to do is understand what an ANOVA really is. We know that ANOVA stands for Analysis of Variance, but we also need to understand which types of variance we will be analyzing. Once we spend a significant amount of time analyzing these variances and calculating them using very wicked formulas, we need to have a logical way to keep track of all of these calculations, and so the way that we do this is by keeping them in an ANOVA source table. So that's the other thing that we're going to be talking about. Once we conceptually understand what an ANOVA is and how we calculate the different types of variance, we're going to revert back to our 7 steps of hypothesis testing, which are ultimately geared to figure out whether our hypotheses are significant or not. So we will talk about how we can find significance and identify it using the one-way ANOVA. Once you incorporate ANOVA into your hypothesis test, there is an extra step that we're going to have to do, which is called the post hoc analysis. Now, the post hoc analysis doesn't happen when you do a one sample t-test or an independent versus dependent samples t-test. No, the post hoc analysis happens only once you have an ANOVA, a one-way ANOVA, a two-way ANOVA, a three-way ANOVA, or a multivariate analysis of variance. So this is going to be the first time that we've actually mentioned anything similar to a post hoc analysis. And as is customary with all the episodes of Once Upon a Lecture, we will work through some ANOVA examples together. So without further ado, let's talk about what is ANOVA. If you recall, previously, we have been using t-tests to compare samples to a population or one sample to another. However, in both situations, we were comparing two groups to each other. But what happens if we want to compare more than two groups? Well, in this case, we will no longer be using a t-test, we will be using an ANOVA. ANOVA is an acronym for Analysis of Variance. So you can think of an ANOVA as an extension of a t-test. And again, when using t-tests for comparisons, we looked for differences between the means or the averages of the two groups. But when using an ANOVA, we will be looking at the variance of each group to make comparisons. The reason behind using variance versus averages is a long story, much older than you or me, which, let's be honest, none of us have any time to get into right now. But what you should understand is that variance has certain properties that allow us to analyze for overall effects between these different groups. So when you hear the expression one-way ANOVA, that means that the analysis will have one independent variable with more than two levels. So thinking back to the one sample t-test or any t-test in general, we used to compare samples to each other in which we had one independent variable with only two levels or groups. We know that in order to make a comparison, the minimum number of groups we need to have is 2. In some instances, one group would be the control group and another group would be the treatment group. Or, for example, you can have one group receiving one level of the independent variable and the other group receiving a different level. So we always needed to have a minimum of 2 groups to make a comparison. When it comes to an ANOVA, we are going to have more than 2 groups. You can also have something called a two-way ANOVA. In a two-way ANOVA, you would have two independent variables. So the minimum number of groups any variable must have is 2. If each independent variable has a minimum of 2 groups, and we have 2 independent variables, 2 times 2 would give us a possible comparison of 4 different groups or 4 different levels. We're not going to get into the two-way ANOVA in this lecture. We're going to start by talking about the one-way ANOVA. So just as a reminder, the one-way ANOVA has 1 independent variable with more than 2 groups. So you may be thinking, Maleficent, why wouldn't we just conduct a series of t-tests instead of coming up with a completely new analysis called an ANOVA when we have group differences that exceed 2 groups? Well, that is a great question. Whenever we conduct any type of hypothesis testing, we need to be aware that we will always have a certain amount of possible error. Typically, that error is set to 5% or 0.05. It can sometimes be less than 5%, but never more. So if you think back to step 3 of hypothesis testing, we usually set our alpha level at 0.05. That means we're willing to accept 5% chance of error and 95% chance of accuracy being correct about our decision. So now imagine that you have 3 groups that you want to compare, and you're going to run a separate t-test for each paired comparison. These possible comparisons would include comparing group 1 versus group 2, group 2 versus group 3, and group 1 versus group 3. So if we were to combine all the possible pairwise comparisons, it looks like we have 3 possible combinations. Now, if each t-test is going to give us a 5% chance of error, 5% error multiplied by 3 different t-tests is going to inflate our error to 15%. And no research study is going to be acceptable with that much error. So, to answer your question about why we don't just conduct a variety of different t-tests, it's because that will inflate our error. Running multiple t-tests for the same research question inflates your error from 5% to 15%, 20%. It really depends on the number of groups that you are comparing. So with an ANOVA, we run 1 analysis, only 5% chance of error, and in a way that we can compare all of the groups at once. So instead of running 3 different analyses, we run 1 analysis that takes into the consideration all of the group differences, all while keeping us at a totally legitimate 5% chance of error. So the next thing that we need to revisit is the topic of between subjects versus repeated measures design. You may remember that when we were discussing t-tests, we learned about 2 types of samples, the independent sample and the dependent sample. We know that participants who are not related to each other in any way and who are randomly selected and randomly assigned to a condition are going to be analyzed using a between subjects design or an independent samples t-test. However, participants that are closely related, or better yet, if you're testing the same participants over time, more than once, then we would be using a within subjects design, also known as repeated measures. And when we have 2 of those groups, we use the dependent samples t-test. So when we analyze data using an ANOVA, we use the exact same criteria to determine if our analysis will be between subjects or repeated measures. Let me remind you that the reason we use different types of analyses is to account for the differences in the variance for each type of sample. Remember, the amount of individual differences between 2 people will always be bigger than the amount of difference between the same person and him or herself over time. Therefore, we have different formulas that properly account for these varying levels of individual differences. In other words, it wouldn't be fair to compare apples and oranges, so we want to make sure that we're comparing apples to apples, right? If we have a within subjects design, we're going to compare the participants to themselves, And if we have apples and oranges, which is a between subjects version of that design, then we're going to have a much larger variance, which will be accounted for with different calculations in the formulas. So now that we've refreshed our memory on between subjects versus repeated measures design, let's take a look at the different types of variance that are part of our ANOVA, part of this analysis of these variances. Since ANOVA means analysis of variance, let's take a look at the different types of variance that exist in our data. The first type of variance we're going to look at is called between group variance, the degree to which the groups differ from one another. This variance captures our desired effects or treatments or manipulations of the independent variable. So the between group variance is going to tell us how the groups differ based on the different levels of the independent variable. We want this variance to be large. We want to see these scores vary, because if they do, then it will show that our independent variable is actually having a significant effect on the dependent variable. In other words, if we see this variance being large, we can attribute the difference to the different levels of the independent variable and not due to chance or coincidence. Within group variance is the second type of variance we'll talk about, and this is the variance that tells us how the individual scores differ from others within the same group. And this variance captures individual differences as well as experimental error. So remember, we can never be 100% certain of our decisions, and so we do account for that in our variance formula, but not in the between group variance. We account for that in the within group variance. So within group variance is also known as error variance. We generally do not want this variance to be large because we want the participants within the same group to be more similar to each other. If the variance within the groups is large, then that will suggest that there is a high amount of individual differences or a high amount of error. So generally, we want between group difference to be large and within group variance to be small. We also have a variance called subject variance, and the subject variance is relative only when using repeated measures ANOVA. So you will never be calculating subjects variance if you have a between subjects design. We only calculate subjects variance if we have a repeated measures design, and this variance captures the degree to which each person differs from themselves over time. The last type of variance we have is the total variance, and total, just as it is in any other mathematical calculation, is the sum of all the other variances. So the total variance represents all the possible sources of variance added together. So let me give you an example so we can really understand how the different types of variances apply to a possible research question. Let's imagine as Queen of the Moors, I'm interested to see if the weather has any effect on the mood of the creatures who live in my kingdom. So I will be using an ANOVA, which means I'm going to have more than two groups of types of weather. So if my independent variable is weather, I'm going to come up with 4 different types of weather conditions. The first one will be sunny. The second one will be windy. The third one will be snowy, and the fourth one will be foggy. So we have sunny, windy, snowy, and foggy. I have 4 levels of my independent variable, but I still only have one independent variable, which is weather. What I'm interested in measuring is the mood of the inhabitants of the moors. And let's say that will be measured on a 5-point scale, 1 being very unhappy and 5 being very happy. So what I'm going to do is I'm going to administer this happiness scale across all these different types of weather conditions. The between group variance would be the differences in mood ratings that I see for people who took the scale when it was sunny, compared to people who took the scale when it was windy, compared to people who took the scale when it was snowy, and who compared to people who took the scale when it was foggy. So the scores between the 4 weather conditions should be different, according to my hypothesis, in order to prove that weather is in fact playing a role in the mood of the inhabitants. Within group variance would pertain to the scores within each specific weather condition. So for example, if I had 30 participants take the scale in a sunny condition, another 30 participants take it in a windy, snowy, and foggy condition, the within group variance compares the 30 people within the sunny condition to each other. It compares the 30 people in the windy condition to each other. So essentially the within group variance is comparing the data points only among that particular group. This is opposite of the between group variance, because for between groups we're comparing across the conditions, windy, sunny, windy, snowy, foggy. And for within group variance, we're comparing the differences within each condition. If I had a repeated measures design, I would have all of the inhabitants take the scale when it was sunny, then the same inhabitants would take the scale when it was windy, and they would also take it when it was snowy and foggy. So repeated measures means I'm repeatedly measuring the same participants across a variety of different conditions. If I want to see how those participants changed across time from the sunny, windy, snowy, and foggy conditions, that would be my subject variance. I would compare each person, each participant, each inhabitant to him or herself across each of those conditions. So that's how subject variance would work. And the total variance would be adding up the between group, within group, and subject variance to receive my total variance. So each type of variance has a corresponding formula using what is called the sum of squares. Whenever we multiply a number by itself, we call that squaring. So if you recall, when we calculated variance for t-tests, we squared each score and then added up the sum of all of those squared values, aka the sum of squares. So let's take a look at the formulas for the different types of variance we have. For between group variance, we have the sum of x of each group added together divided by n, the total number of people within each sample. Ultimately, we're going to add all of those together and subtract from the total sum of the scores divided by the total number of people in the entire experiment. For within group variance, we do something very similar to the variance formula that we used when we conducted the t-tests. So you can see the sum of x squared minus the sum of x then squared divided by n. So we would do this for each sample relative to how many conditions you have of your independent variable. The subject variance, which again I will remind you is only for repeated measures design, is taking the sum of each person's score across all the different conditions and dividing by k, which we will learn is the number of groups that exist in your ANOVA experiment. So in the weather example that I just gave you, we had 4 different types of weather conditions, so k would be 4. K represents the number of levels you have of your independent variable. And for total variance, you can either add up all the variances together or you use the standard formula that we've been using for variance, the sum of x squared minus the sum of x then squared over n. Don't worry, I know what you're thinking. That's a lot of formulas. There are some new symbols in there. We will work through all of these examples together momentarily. I just want to make sure that we conceptually understand what we're working with here. All right, so the next thing we're going to do is talk about the ANOVA source table. In order to keep track of all of the values that we calculate for each type of variance, we are going to log them into what is called an ANOVA source table. Here's an example of a source table for between subjects ANOVA. So on the left-hand side, you see source. Remember, the 3 different sources of variance we have for a between subjects ANOVA is going to be between groups variance, within group variance or error, and the total variance. Beside that, you see a column that says SS. SS stands for sum of squares. So those formulas that I just showed you, once you calculate those for each type of variance, the final number would go here under sum of squares. Then you have a column for DF. DF should look familiar to you because that is degrees of freedom. Degrees of freedom for between group variance is K minus 1. K represents the number of levels you have in your independent variable. So once again, in the weather example I just gave you, we had 4 different types of weather conditions. Therefore, K would represent the number of groups. So K equals 4. And K minus 1 would give us 3. For within group variance, we take the N, the total number of people in our data set, minus K, the number of groups. And for total degrees of freedom, same as always, it's going to be N minus 1. Now let's move over to the mean squared column. Mean squared column is obtained by dividing the sum of squares for that variance by the degrees of freedom for that variance, and ultimately you will get the mean squared. So for example, if I want to find the mean squared for between group variance, I'm going to take the sum of squares between groups divided by degrees of freedom between groups to get mean squared between groups. I will do the same thing to get mean squared of within group variance. I'm going to take the sum of squares within groups, divide by degrees of freedom within groups to ultimately get mean squared within groups. And this step is the most important because it is going to help us calculate our F value. Whoa, now we have an F value? That's right. So previously when we were doing t-tests, we had t values. For ANOVA, we're going to calculate an F value. So another way to say ANOVA is an F test. So the F computed value is obtained by dividing the mean squared between groups by the mean squared within groups. So ultimately, once you do that, you are left with your F computed value. So that was the source table for between subjects ANOVA. Now let's take a look at the source table for repeated measures ANOVA. So it's similar to the between subjects one, but because we have to add one more type of variance, the subject variance, the table is going to slightly change. So let's take a look at this table. For sources of variability, you have between groups, now you have subjects, and then you have within groups error variance and your total. So for between group variance, your degrees of freedom are calculated the same, but you will notice that for subjects, we have S minus 1. S represents the number of subjects within each condition. So for example, if I had 10 participants that experienced all 4 types of weather conditions and they reported their mood in each one, I would have 10 minus 1, which would give me 9. So S represents the number of people in each condition. For within group degrees of freedom, you have K minus 1, which is the number of groups minus 1. So 4 minus 1 gives us 3. And S minus 1 is the number of participants within each condition. So that was 9. So we have 3 times 9, which would give us 27. And then total N minus 1 is the total number of people you had in the entire data set. You will notice that for mean squared, we calculate it the same way, and we only calculate mean squared for between group variance and within group variance. So even though we're separating the subject variance, the individual differences from the error variance, we actually don't do anything else with that value. So to calculate F, once again, you're going to divide mean squared between groups by mean squared within groups. So just to reiterate, the whole purpose of calculating subject variance when doing repeated measures ANOVA is to make up for that difference of individual differences. So remember when I told you that when we compare different people to each other, the variance will be larger than if we compared the same people to themselves over time. So naturally, we are going to be more similar to ourselves over time than we are to someone else within the data set. So in other words, what we need to do is weed out that difference where we're comparing ourselves to ourselves and separate that from the error variance, which represents the individual differences among other people in the condition. So you can think of subject variance as a type of filter, which accounts for different levels of individual differences, when you're calculating within group variance. So when we do our calculations and we're trying to compute F, at the end of the day, what we are interested in is between group variance and within group variance minus that subject variance. So once you filter out the subject variance from the error variance, you no longer need to do anything else with that value. Your F computed value will still depend on the ratio of mean squared between to mean squared within, also known as mean squared error. So how do we find significance when it comes to an ANOVA? To determine if the results of an ANOVA are significant, we go back to our same 7 steps of hypothesis testing. The first step is to state the null hypothesis. Because we now have more than 2 groups, our null hypothesis will have to reflect that there are no differences between any of the groups. So whether you have 3 or 4 or 5, the null hypothesis just says that the groups are not equal to each other, regardless of how many there are. The alternative hypothesis would say that there are significant differences between the groups. So this means that the differences can exist between as many or as few groups as possible. The alternative hypothesis does not specify to us between which groups the differences exist. It's just telling us that we feel like there are going to be differences between the groups. Step 3 is to set alpha to 0.05. That does not change. And now we have step 4, the rejection rule. We typically set the rejection rule based on degrees of freedom, if you recall. For ANOVA, each source of variance has its own degrees of freedom. So you will actually have to find 2 values for degrees of freedom, one for between group variance and one for within group variance. And so if you recall, for independent and dependent t-tests, we calculated a t-computed value, and then we compared it to a t-critical value that we found in a chart based on degrees of freedom. For ANOVA, we're going to be calculating the f-computed value and comparing it to an f-critical value that we find in now a new table. So if we look at this table, we can see that the degrees of freedom for within group variance are listed vertically from top to bottom, as is labeled by the label above the column, df subscript w. Degrees of freedom for between group variance are listed horizontally from left to right. As we could see, it says degrees of freedom associated with the numerator df subscript b. So now we need to find 2 different degrees of freedom and see where they align in order to find our critical f value. You can also see that you have 2 rows of numbers for each line. You have 5% and you have 1%. These percentages correspond to your alpha level. If you set alpha to 5%, you're going to be looking at the 5% line. If you set alpha to 1%, then you would be looking at the 1% line. For the purposes of this lecture, we are going to use the 5% line because we by default set our alpha to 0.05. So ultimately, our F critical value will be based on a combination of degrees of freedom within and degrees of freedom between. All right, so now that we know how to find our rejection rule and our F critical value, the next step is to compute F. F is computed in the source table I just showed you, ultimately by dividing the mean squared between over mean squared within. Step 6, as usual, is to make your decision. Now, to make the decision about the null hypothesis, we're going to compare the absolute value of the F computed value, which we obtained in step 5, to the absolute value of the F critical value we found in step 4. Same rules apply as they have been applying for t-tests. If the F computed value is greater than or equal to F critical, we're going to reject the null and conclude that there are differences between the groups. If F computed is less than F critical, then we're going to fail to reject the null and conclude that there are no differences between the groups. And as usual, step 7 is to write your conclusion. So up until now, those are the 7 steps that you're familiar with because you've been doing them for a significant amount of time. But now I'd like to tell you about the post hoc analysis. This is fairly new information, and the post hoc analysis is typically conducted kind of as a step 8 after you've written your conclusion. So imagine that you conducted hypothesis testing to compare the variances of 3 different groups. You calculated that F computed is larger than F critical. So you conclude that there are differences between the groups, but now you want to determine if the differences existed between only 2 of the groups, or 1 of the groups, or between all of them. So the significant F test tells us that there are differences, but it doesn't tell us where between which groups those differences are. So if you have 3 groups to compare, how many possible combination of differences can there be? Well, we can have a difference between group 1 and group 2, group 1 and group 3, and also group 2 and group 3. So there are 3 possible places that those differences can exist. To determine specifically in which groups the differences occurred, the researchers need to conduct a post hoc analysis. So calculating the post hoc analysis is very similar to the 7 steps. The first thing we would need to do is calculate the differences for each pair of means. So when we say difference, we mean subtraction. Mean 1 minus mean 2, mean 1 minus mean 3, and mean 2 minus mean 3. These represent all the possible combinations of differences that could exist in our particular research question. The next thing we have to do is calculate a critical value for the post hoc analysis based on a specific formula. Once we find that critical value from the formula, we're going to compare each difference that we've calculated above to this new critical value that we've obtained using a special formula. If the difference that we've calculated among the means is greater than the critical value, then the difference between those 2 groups is significant. But if the difference is smaller than the critical value, then the difference is not significant. So then we're going to follow that up with a more detailed conclusion statement with specific explanations about which groups were significantly different and which groups were not significantly different from each other. So we have 2 different types of post hoc analyses. The first one is called the Fisher LSD. And LSD, contrary to what you're thinking, stands for least significant difference. The second test we have is called the Tukey HSD, and HSD stands for honestly significant difference. So while you can use both of them for a post hoc analysis, you can only use the Tukey test if you have an equal number of participants in each group. In other words, if you have an equal sample size. And the Tukey test is a more stringent test, which means it's more strict, given that the formula that goes along with it will always give you a higher critical value than if you use the Fisher LSD. So if you have a higher critical value, it means that the differences among the means will also need to be higher in order to prove that there in fact were differences between those 2 groups. So if you want a stricter test, and if you have equal sample size, you can go with the Tukey test. Otherwise, you can use the Fisher test, which can be used if you have unequal sample size in the groups. So for example, going back to the weather question on mood and how that is affected by different weather conditions, I have 4 different levels in that case. But what if I had 10 people take the survey in a sunny condition, but only 8 people took it in the windy condition? In one group I have 10, in another group I have 8. So that would be an unequal sample size for both groups. Therefore, I would not be able to use the Tukey test, and I would have to use the Fisher test. All right, now that we've gotten a grip conceptually on this information, let's actually look at some concrete examples with some numbers so that we can calculate these together and really apply the concepts to the arithmetic. Example number 1. Before I enacted my sleeping curse on Aurora, I decided to conduct some research on the power of hypnosis. We know that some people are more susceptible to hypnosis than others, and that they have a vivid imagination and fantasy life. This led me to hypothesize that the ability to recall dreams will also be affected by hypnotic susceptibility, which we're going to call HS. Using Maleficent's scale of hypnotic susceptibility, I created low, medium, and high susceptibility groups by selecting from volunteers who took my assessment. Then I asked the volunteers to keep a dream diary for 1 month. At the end of the month, I collected the diaries and counted the number of dreams each person recalled. I want to see if the groups differed in the number of dreams they recalled based on their level of hypnotic susceptibility. Here are the data that I found. So we have 3 different categories: low, medium, and high susceptibility. And the numbers that you see here represent the number of dreams that each group has recalled. The first thing I need to do is identify if this is between subjects or repeated measures design. Well, I know that repeated measures means I would have had to test the same people more than once. In this case, the people who were low hypnotic susceptibility were different than the people who were high hypnotic susceptibility and different from the medium hypnotic susceptibility group. In this case, the participants are not related to each other in any way, and they did not submit multiple diaries. They only submitted it once, so they were not measured more than once over time. So to me, it looks like this is an independent or between subjects design. What is the independent variable? Well, if I believe that hypnotic susceptibility is going to affect the number of dreams my participants recalled, that would mean that the independent variable is hypnotic susceptibility. How many levels does it have? Well, I have low, medium, and high, so that looks like 3 different levels. How many groups am I comparing? I am comparing 3. So the number of groups you are comparing will always match the number of levels your independent variable has. Because I have 3 different levels of hypnotic susceptibility, I am comparing these 3 groups to each other. And what is my dependent variable? What is it that I'm measuring? I'm trying to see if the number of dreams they recalled is in any way related to the levels of hypnotic susceptibility. Great. Now that I've identified this is a between subjects design, I know that I need to calculate 3 types of variance: between group, within group, and total. To do this, I need to calculate the sum of squares for each level of my independent variable. So first I'm going to set up an x squared column for each group. I'm going to have low hypnotic susceptibility, and right beside it I'm going to say low squared. Then I'm going to have medium hypnotic susceptibility and a squared column for that, and a high hypnotic susceptibility and a squared column for that. Once I calculate the squared values for each score in my list, I'm going to sum each column to get the sum of squares for low, medium, and high hypnotic susceptibility. If I square each score, these are the values that I get. 4 times 4 is 16, 9 times 9 is 81, all the way down for low hypnotic susceptibility. I do the same thing for medium. 14 times 14 gives me 196, 12 times 12 gives me 144, all the way down that column. And then I do the same thing for the high hypnotic susceptibility. 22 times 22, 26 times 26, until I complete that. Remember, the next thing we do after we have all of these values is to get the sums. So you want to get the sum for every column on this chart. Once I add up the sums of each column, these are the values that I get. The sum of the low group is 75. The sum of the low square group is 813. The sum of the medium group is 111. The sum of the medium group squared is 1,925. The sum of the high group is 157, and the sum of the high squared group is 3,271. The next thing I'm going to do is identify the n for each group. It looks like in this case I had equal sample size. It looks like I had 8 participants in each condition. 8 were in the low hypnotic susceptibility, 8 different people were in medium hypnotic susceptibility, and another 8 were in the high hypnotic susceptibility. So the next thing I'm going to do is I'm going to calculate the mean or the average for each group. We know that the way we calculate the mean is the sum of x divided by n. So once I do that, I have the mean for the low hypnotic susceptibility is 9.38 dreams recalled. The mean for medium hypnotic susceptibility is 13.88 dreams recalled. And the mean for The high hypnotic susceptibility is 19.63 dreams recalled. So we do see a pattern here. It seems that as hypnotic susceptibility increases, so does the number of dreams the participants recall. Are these differences significant? We don't know yet. This is something that we will need to test using hypothesis testing. So there's one more piece of information that we need to calculate, and that is the totals for all of these values. So we need to find the total sum of x, the total sum of x squared, the total n, and the total mean for all of the groups. So if I add up 75 plus 111 plus 157, that's going to give me the total sum of x. If I add up the total sum of x squared for the low, medium, and high squared groups, I'm going to get 6,009. Now, if I had 8 people in each condition and I had 3 conditions, 8 times 3 will give me a total n of 24. And by taking the total sum of x, 343, by our total n, 24, I'm going to get a total mean of 14.29. Now that we have all of our sum of squares values for each group, we're ready to calculate the variance for our source table. Because this is a between subjects design, we only need 3 different sources of variability. We need between groups, within groups, and total group variance. Let's start with sum of squares between groups. We know that these are the values we've just calculated from our chart. What we need to do now is plug them into our sum of squares between formula. So the sum of x of the first group, of the low hypnotic susceptibility group, is 75. And we divide that by the n of that group, which is 8. So we have 75 squared over 8. In the second position, we have the sum of x of the medium hypnotic susceptibility group, which is going to be 111. So we do 111 squared over 8 because there were also 8 people in that sample. The third group we have is 157, the sum of x of the high hypnotic susceptibility. We square that and we divide that by 8 as well, because once again, the high hypnotic susceptibility group also had 8 participants. Once we have all of those added together, we are going to subtract it from the sum of x total. We know that the sum of x total was 343 squared, and we know that because there were 8 participants in 3 different conditions, our total n is going to be 24. So we're going to have something that looks like this once you plug in the values into the corresponding slots of the formula. The next thing to do is just to simplify it. Once we simplify that second row, we get 703.13 plus 1540.13 plus 3081.13. All of that added together is going to give us 5,324.39, which we're going to subtract 4902.04 to ultimately be left with a sum of squares between variance equal to 422.35. This is the value that we're going to put in our source table for sum of squares between. Nice work. The next thing we're going to do is calculate the sum of squares for within group variance. So once again, using these numbers that we've calculated, we have to plug them into our formula. And here is what that formula looks like. We're going to take the sum of x squared of the low hypnotic susceptibility group, which is 813, and we're going to subtract it from the sum of x for that same group, which is 75. 75 squared over 8, which may seem familiar because we just did it in the sum of squares between group variance. You're going to do this for the medium hypnotic susceptibility group as well. So the sum of x squared for the medium hypnotic susceptibility group is 1,925. We're going to subtract that from 111 squared over 8. Then you're going to do that for the third group, which is the sum of x squared for the high hypnotic susceptibility group, which is going to be 3,271 minus 157 squared over 8. So once you plug in the values where they go, this is basically what you should be left with. And if we continue simplifying that further, we should get 109.87 plus 384.87 plus 189.87. If we add all of those together, we are ultimately left with the within group variance of 684.61. This is the value that's going to go in our source table for sum of squares within groups. So far we have sum of squares between groups and sum of squares within groups. We know that total variance is going to be the sum of between plus within. So once you calculate that, once you add 422.35 plus 684.61, you are left with 1,106.96. So now let's move over to the degrees of freedom column. We have K minus 1 is the degrees of freedom for between groups. Remember, K represents the number of levels you have in your independent variable. Our independent variable was hypnotic susceptibility. So we had low, medium, and high. That means we have 3 levels, or K is equal to 3. 3 minus 1 is going to give us 2. So degrees of freedom for between groups is 2. The next thing we need to do is calculate N minus K for degrees of freedom within groups. N minus K is going to be 24 minus 3. 24 is the total number of people in our sample. 3 represents the number of levels we have for our IV. 24 minus 3 gives us 21. So 21 represents the degrees of freedom for within group variance. And last but not least, we have degrees of freedom for total, which is going to be N minus 1. We had a total of 24 participants. 24 minus 1 gives us 23. Moving right along to the mean squared column, we know that mean squared is calculated by sum of squares between divided by degrees of freedom between. So if I take 422.35 and I divide it by its corresponding degrees of freedom of 2, I am left with 211.18. So my mean squared between value is 211.18. I'm going to do the same thing for within group variance. I'm going to take 684, divide that by 21, and I'm going to be left with 32.60. The last thing I need to do is calculate my F value. My F value is calculated by dividing mean squared between 211.18 by mean squared within 32.60, and I'm ultimately left with an F value equal to 6.48. This number, this F computed value, 6.48, is going to be compared to an F critical value, which I'm about to find. If this number that I've computed is larger than the critical value, my decision would be to reject null. If this value is smaller than the F critical value I find in the table, then I'm going to fail to reject null. All right, now that we found F, let's go ahead and jump into our 7 steps. Step 1, state the null hypothesis. Our null hypothesis will say the number of dreams recalled does not depend on hypnotic susceptibility. In other words, the level of hypnotic susceptibility of participants had no effect on the number of dreams recalled. Step 2, to state the alternative, says the exact opposite. The number of dreams recalled does depend on hypnotic susceptibility. In other words, the hypnotic susceptibility of participants does affect the number of dreams they recalled. Step 3 is setting alpha to 0.05 as usual. Step 4 is finding our threshold, our rejection rule. In other words, finding F critical. We know that in order to do this, we're going to need degrees of freedom between and degrees of freedom within. So if we look back at our source table, we know that degrees of freedom between groups is 2 and degrees of freedom within groups is 21. So looking at my chart here, what I'm going to need to do is find degrees of freedom between of 2, which is located horizontally, and degrees of freedom within of 21, which is we can find vertically. So if I look at where those 2 points intersect, I can see at the 5% error line that F critical is equal to 3.47. So once again, I went across to 2 because that represented degrees of freedom between, and I slid my finger down to 21 to represent degrees of freedom within. I found the number that occurs at the intersection of those two axes, and I see two numbers. One number is 5.78 and the other number is 3.47. Because I've set alpha to 0.05, I'm going to use the critical value at the 5% line, which in this case is 3.47. So we've identified our F critical value as 3.47. We also previously computed F to be 6.48. So now we're ready for step 6, the decision. If the absolute value of F computed is greater or equal to F critical, we know that we reject null. Conversely, if F computed is smaller than F critical, we fail to reject null. According to this, it looks like 6.48 is definitely bigger than 3.47, so our decision will be to reject the null. And our conclusion statement would say that there is a significant difference in the number of dreams recalled based on hypnotic susceptibility, comma. Now this will no longer be T, this will be F because this was an F test. In the parentheses, you will have to include degrees of freedom for between, comma, degrees of freedom within equals your F computed value. After that, you will put another comma, and P will be less than 0.05 if you reject null, and P will be greater than 0.05 if you fail to reject null. So it's a similar process to how you would report T values, but now you have F instead of T, and you also have 2 degrees of freedom instead of just one value in the parentheses. Otherwise, the rule, the procedure for the greater than or less than P value stays exactly the same as it did for the t-test. So our decision was to reject the null and conclude that hypnotic susceptibility did affect the number of dreams people recalled. But where specifically were these differences? Were they between the low hypnotic susceptibility group and the high hypnotic susceptibility group? Were they between the low hypnotic susceptibility and medium hypnotic susceptibility group? Or were they between the medium and high hypnotic susceptibility groups? Well, to answer this question, we're actually going to have to run a post hoc analysis. Let's start with the Fisher LSD post hoc analysis. The first thing we need to do is calculate the means for each of our groups. When we previously did this, we found that the means for the low hypnotic susceptibility group was 9.38, the mean for the medium group was 13.88, and the mean for the high group was 19.63. The next thing we need to do is find the differences between all possible pairwise comparisons. So we can compare the low and the medium group, the low and the high group, and the medium and the high group. If I subtract the low minus the medium group, I get a difference of negative 4.5. If I subtract the low minus the high susceptibility group, I get a value of negative 10.25. And if I take the difference of the last one, the medium minus the high susceptibility group, I get negative 5.75. So using the Fisher LSD formula, we need to find the critical value against which we're going to compare these mean differences that we calculated above. So this is the formula for the LSD post hoc analysis. We have LSD at the 0.05 level, representing 5% error, is equal to a t-value at the 0.05 level multiplied by the square root of mean squared within times 1 over the n of the sample of the first group plus 1 over n of the sample of the second group that is being compared. In our case, we have equal sample size and each group had 8 participants. So according to the formula, we will need to know the mean squared within group value, which we can obtain from our source table. We can see that that value is 32.60. We also need to find the t critical value using the t table for degrees of freedom of 21. So we basically are going to use the mean squared within value and the degrees of freedom within value. So to find that t critical value using our degrees of freedom within, we're going to revisit our critical values of t chart. This should look familiar to you because you've used it multiple times when calculating the t-critical value for your independent and dependent samples t-test, and also for your confidence intervals. So if our degrees of freedom are equal to 21, and we're concerned at the 5% error level, we're going to slide our finger down to 21 and across to 5%, and we can see that that t-critical value is 2.0796. So this is the value that we're going to plug into the LSD formula. So we have found that the t-critical value is 2.0796. If we plug these values into the formula, we have t is equal to 2.0796 multiplied by the square root of 32.60 times 1 over 8 plus 1 over 8. Once you simplify that, you are going to get the 2.0796 multiplied by the square root of 8.15. Simplifying that further, we get a critical value of 5.94. So 5.94 is our critical value. We're going to compare each mean difference to this number. If the mean differences that we've calculated are greater than this value, then we can conclude that there are significant differences between those groups. If the mean difference is smaller than this, then that means that that particular comparison does not have any significant differences between the groups. All right, here comes the fun part, the comparison. So on the left-hand side, we see the pairwise comparisons, and on the right-hand side, we see the LSD value, which we've just calculated. You're going to use the same critical value for all of them. The only instance in which the critical value would change is if you conducted the formula and ran the LSD test more than once. And the only reason that you would do that is if you had one group that had 8 participants and one group that had 7 in a comparison versus one group that had 8 and another group that had 8. That would definitely change your LSD value. In this case, because we had equal sample size, we only had to find one critical value, and we're going to compare our mean differences all to 5.94. So we ask ourselves the question, is the absolute value of 4.5 greater than or less than 5.94? So you may think to yourself, that's less than. So there are no significant differences between the low and medium hypnotic susceptibility groups in the number of dreams recalled. Then we look at the absolute value of 10.25 compared to 5.94. That one looks greater. So because it's greater, we will conclude that there are significant differences in the number of dreams recalled between the low and high hypnotic susceptibility groups. And then we look at the last comparison, medium versus high, gives us a value of 5.75. Very close, but not quite larger. So it is also going to be less than, concluding that there are no differences between medium and high hypnotic susceptibility. So given the fact that only one of these was greater, that's a good sign to us that because of the low versus the high hypnotic susceptibility group, our ANOVA was actually significant. So there were no significant differences in the number of dreams recalled between the low and medium susceptibility groups or between the medium and high hypnotic susceptibility groups. However, there were significant differences in the number of dreams recalled between the low and high hypnotic susceptibility groups. Those who scored higher on hypnotic susceptibility remembered significantly more dreams. Now let's take a look at the second type of post hoc analysis we have, the Tukey HSD. The Tukey HSD post hoc is more strict, and again, it can only be used if we have equal sample size in all groups. In our case, we are in luck. We had 8 participants in all of the conditions, so we are okay to use the Tukey test. We start the Tukey test the same way as the Fisher, by finding the differences between all the possible pairs of means. So previously we found the mean for the low, medium, and high hypnotic susceptibility groups, and we also found the differences between them. So this is exactly what we just did for Fisher. So far things are staying the same. Where they start to become different is in the formula. All right, so now instead of LSD, we have HSD at the 0.05 level is equal to Q. What? Q? There's a Q now. First there's an F and now there's a Q. I know, I told you this was going to be a challenging lecture. But yes, now we're going to have to find a Q critical value and multiply that by the square root of the mean squared within divided by the number of people in each group, which is 8. So to find the critical Q value, we're going to use a Q chart. As you will notice, in order to find that critical value, the Q chart asks us to identify the degrees of freedom within and the mean squared within value. We will also need to know what is K. K represents the number of groups. Once again, this number is 3 because we have 3 different levels of hypnotic susceptibility. So to find the critical Q value, we need to find the number of groups horizontally and degrees of freedom within vertically. According to our source table, we know that degrees of freedom within is equal to 21, mean squared within is equal to 32.60, and K is equal to 3. So I'm going to find 3 horizontally across the top, and I'm going to slide my finger down vertically until I see 21. Once again, I see 2 values here. One says 0.05, one says 0.01. Because we're calculating at the 5% level, we're going to look at the number at the 0.05. So I can see that that number is going to be 3.58. Once again, across the top, you slide your finger to 3, and you slide it all the way down to 21. 3 represents the number of groups. 21 represents degrees of freedom within. The place where those two numbers intersect is the number 3.58. 3.58 is going to be my critical Q value, which I'm going to plug in to my formula. So Q is 3.58. I'm going to multiply that by the square root of mean squared within, which is 32.60, divided by n in each group, which is 8. If I simplify that further, I get 3.58 multiplied by the square root of 4.075. Once I solve for that, I get 7.23. 7.23 is my critical Tukey HSD value. I'm going to compare each mean difference to this particular number. If the difference that I've calculated is greater than this critical value, we conclude that there are differences between the groups. If my mean differences are smaller than this critical value, we conclude that there are not differences between those given groups. Let's see what happened. Once again, I'm going to do a comparison of the absolute value of my means that I've calculated and the critical HSD value. And so is the absolute value of 4.5 greater than or less than the HSD value of 7.23? Looks like it's less than. Then I'm going to compare the low and the high group. I get an absolute value of 10.25. 10.25 is in fact greater than 7.23. And last but not least, medium versus high susceptibility group gives me an average difference of 5.75. That also is less than my critical value. So once again, there was a significant difference in the number of dreams recalled depending on hypnotic susceptibility. More specifically, differences were found between low and high hypnotic susceptibility, but not between low and medium or medium and high susceptibility groups. So you see, we've come full circle. We've done a between subjects one-way ANOVA. We found that F was significant. We found significant differences between the groups. And then using a post hoc analysis, we were able to identify between which groups specifically those differences were. Is it possible that all of the groups would have a difference? Yes. Is it possible that none of them would have a difference? It's possible, but if that happened, we would have failed to reject null, in which case you would not be doing any post hoc analysis, right? A post hoc analysis is conducted only if you reject null. Only if you conclude that there were differences somewhere among the groups. All right, let's try one more example. An experiment was performed to determine the effects of taking a magic class on the ability to perform simple magic tricks. 10 students were given a 20-item magic test at the beginning of the course, immediately after the course, and 6 months after the course. The data represent the number of magic tricks they completed correctly each time. Did experience with the magic course affect their performance? So here are the data that we've collected. Before, after, and 6 months after, and the numbers in each column represent the number of magic tricks they completed correctly. So the first thing I need to do is identify if this is between subjects or repeated measures. Well, since the same 10 students are taking this magic test before, immediately after, and 6 months after they enroll in a magic course, it sounds like this is a repeated measures design because we are measuring the same participants more than once, repeatedly. What is the independent variable? Well, the independent variable in this case would be time. We have 3 different measures of time: before, immediately after, and 6 months after. And ultimately, we have 3 different levels. So if I have 3 levels, then I will be comparing 3 different groups. And the dependent variable is what I am measuring. I am measuring the number of magic tricks they've completed correctly. So I want to see if the number of magic tricks they can complete correctly before the course is different from the number of tricks they complete correctly immediately after the course, and how that differs or is similar to how many magic tricks they complete correctly 6 months after enrolling in the course. So let's see what happens. Now that I've identified that this is a repeated measures design, I need to calculate 4 types of variance: between, within, subject, and total variance. So to do this, of course, I need to calculate my sum of squares. So similar to what we did with the between subjects ANOVA, what we need to do is take each score that we see here and square it. Once we have each score squared, we are then going to tally up the total. We're going to get the sums of each column. So I set up an x squared column beside each score, and then I square each value. Once I square each score, these are the values that I see. And I know that the next step for me is to find the totals of each column. So if I add up the total of all the magic tricks that they completed before taking the course, I get 100. If I add up the total number of correct magic tricks immediately after the course, I get 135. And then if I tally up the scores that they got 6 months after, I get 125. Now, if I do the same thing and I add up the columns for the x squared values, I get the sum of x squared for before is 1,138. The sum of x squared for immediately after the course is 1,967. And the x squared value for 6 months after taking the course is 1,637. The other thing that I could do is obtain the means for each group. So remember, the formula for the mean is the sum of x over n. Because each group had 10 participants, my n is going to be 10. So I'm going to take 100 divided by 10, and that's going to give me 10. I'm going to take 135 divided by 10, that's going to give me 13.5. And I'm going to take 125 divided by 10, and that will give me 12.5. So I have so far calculated the sums for each group, and now I've also calculated the means. Now, if we look at this column labeled K, K is a new column which we're going to have to add for the repeated measures design. K represents the number of groups or levels that the independent variable has. Because I have 3 different time periods, before, immediately after, and 6 months after, and all of the participants experienced each of those tests, each of those magic tests, I'm going to have 3s going straight down the line for all the 10 participants. If, for example, some participants only took the test before and immediately after, but they never showed up for the 6 months after test, then they would have a 2 in the place of K instead of a 3. But for the purposes of our research question and our data set, all of our participants took all 3 tests. So K is going to be equal to 3 for all of them. Now let's take a look at the column that's labeled the sum of X for each subject. M represents each subject. So if the sum of X represents the total score each person got on all 3 tests combined, it means for student number 1, I'm going to add the score that they got before the course, 10, plus the score they got immediately after the course, 11, plus the score they got 6 months after the course, which is 10. So 10 plus 11 plus 10 is going to give me the sum of the subject number 1, which is going to be 31. Then I'm going to do the same thing for student number 2. I'm going to add their score before the course, immediately after, and 6 months after, which is going to be 12 plus 14 plus 14, and that's going to give me a total of 40. I'm going to do this all the way down for all of the participants, essentially adding every person's score before, immediately after, and 6 months after. Once I create this column of sums across the line for each participant, I am then going to get a sum of this entire column. So in other words, I'm going to add 31 plus 40 plus 49 plus 27 plus 45, etc., all the way down this column until ultimately you get a total of 360. So this represents the sum of each participant's score in total. So this represents the sum of all of the scores of the participants totaled together across all 3 conditions of time. Now that we have all of our sum of squares values for each group, we are ready to calculate the variance for our source table. Remember, the source table for the repeated measures design is a little bit different than it is for the between subjects, because now instead of 3 sources of variance, we're calculating 4. We have between groups variance, subjects variance, which tells us how the participants differed from themselves across time, within group variance, also known as error, and total group variance. So let's start with sum of squares between groups. Using these values, we are going to plug them into our sum of squares between formula. We know that the sum of x for before taking the course is going to be 100. And we know that 10 participants participated in the test before the course, so we're going to have 100 squared divided by 10. We're going to add that to the sum of x of the second group, which is immediately after the course, and that is going to be 135. So we're going to say plus 135 squared divided by 10 again. The third group we have is the 6 months after magic test scores, and the sum of x for group 3 is going to be 125. So 125 squared divided by 10. So once we add all of those together, we're going to subtract from the total sum of x across all of the data points, which is represented by the number 360, and we're going to divide that by the total number of data points we have, which is 30. Because we had 10 participants take the test 3 times, we technically have 30 data points. So once we simplified everything in the first group of brackets, we get 4,385 minus 4,320, and we are left with a variance of 65. This is the value that's going to go in our source table for sum of squares between groups. Now let's find the sum of squares for subjects. Again, these are the values that we have, and so we need to plug them into our sum of squares subjects formula. So that formula looks like this, and I know that we haven't done this one yet, so let's take a moment and just understand what the symbols are telling us. We know that we need to find the sum of all of the scores for each subject. Once we do that, we're going to square this value and divide by k the number of groups we have. Once we do that, we're going to subtract it from, once again, the total sum of x, which is 360, divided by the total n we have, which is 30. So this middle part of our formula is actually coming from the sum of x m column that we had in our data set. What we need to do is ultimately take each number for each participant, which is 31, 40, 49, 27, etc. We need to square each value and divide by k the number of groups we had, which is 3. So basically what that means is we're going to have 31 squared over 3 plus 40 squared over 3 plus 49 squared over 3, etc. for all of the 10 participants. So once you do that and you add those together, we are then going to subtract that from the total sum of x of all of the participants combined, which is 360 squared divided by 30. So once we simplify that further, all of the scores squared divided by k added together gives us 4,619.31, which we are going to subtract from 4,320, and we get 299.31. This is the value that's going to go in our source table for sum of squares subjects. The next thing that we can calculate is the sum of squares total. We need to calculate sum of squares total so that we can subtract the subject variance from the total and identify the error variance, or sum of squares within groups. In order to find the sum of x total squared, what we need to do is add up all of the squared values for each of the three groups. So we need to add 1,138 plus 1,967 plus 1,637 to represent the sum of x squared total value. Once we do that, we subtract the sum of x total, which is 360. We square that and we divide by n, the total n, which is 30, since we have 30 different data points. If we simplify that further, we have 4,742 minus 4,320, and we are left with a variance of 422. This is the number that we plug into our source table for sum of squares total. So now that we have sum of squares between groups, sum of squares subject, and sum of squares total, in order to find within group variance sum of squares, all we need to do is subtract. We know that sum of squares within is equal to the total minus the subjects minus the between group variance. So if we take 422, which is sum of squares total, minus 299.31, which is sum of squares subject, minus 65, which is sum of squares between, we are left with 57.67. So our sum of squares for within group variance is 57.67. Let's move over to the degrees of freedom column. We have k minus 1 represents the number of groups. We have 3 different time periods: before, immediately after, and 6 months after, so 3 minus 1 gives us 2. For degrees of freedom subjects, we have s minus 1. S represents the number of people within each group, and so that is 10. 10 minus 1 gives us 9. For within group degrees of freedom, we have k minus 1 times s minus 1. If k minus 1 is 2 and s minus 1 is 9, 2 times 9 will give us degrees of freedom of 18. And last but not least, degrees of freedom total, we have total data points 30 minus 1 is 29. Now we move on to the mean squared column. Even though we've calculated subject variance, we do not need to calculate mean squared for subjects. All we need to do is calculate mean squared for between group variance by dividing sum of squares between 65 by degrees of freedom between 2, ultimately leaving us with mean squared between groups value 32.5. Then we do the same thing for within group variance. The mean squared within groups is going to be the sum of squares, 57.67, divided by the degrees of freedom within, which is 18, ultimately leaving us with the value of 3.20. And for the final and most important step, the f computed value. In order to find f, we need to divide mean squared between 32.5 by mean squared within 3.20. That will leave us with the value of 10.16. 10.16 is going to be our f computed value. We are going to compare this value to our f critical value to ultimately make our decision about the significance of f. So once we start our 7 steps, number 1, state the null hypothesis. Experience in a magic course did not have an effect on students' magic test scores when comparing their performance before the course, immediately after the course, and 6 months after the course. Alternative hypothesis says the opposite. Experience in a magic course did have an effect on students' magic test scores when comparing their performance before the course, immediately after, and 6 months after the course. As usual, we set alpha to 0.05. And now for step 4, the rejection rule. Remember, the rejection rule requires 2 degrees of freedom values, 1 for degrees of freedom between, and 1 for degrees of freedom within. I can see that my degrees of freedom between is 2, and degrees of freedom within is 18. So again, I look at my chart, my critical values of f table, And I need to find degrees of freedom across at 2 and degrees of freedom within at 18. I can see the place that these intersect. It's going to give me a value of 3.55. So my F critical value is 3.55. Moving along with our 7 steps, now that we've identified our rejection rule, let's go ahead and find our computed value. We just calculated the F computed to be 10.16. Now what we need to do is compare our computed value of 10.16 to our critical value of 3.55. 10.16 seems significantly larger than 3.55, so our decision will be to reject the null. And our conclusion statement says that experience in a magic course had a significant effect on the students' magic test scores when comparing their performance before the course, immediately after the course, and 6 months after the course. Comma, F, because now this is an F test, degrees of freedom between 2, degrees of freedom within 18, is equal to your F computed value, 10.16, and P is going to be less than 0.05 because we rejected the null. So the significant F proves that there were differences between the groups, but we would have to conduct a post hoc analysis to identify between which groups specifically those differences lie. In order to identify which groups demonstrated the significant differences in the test scores, I'm going to use the Tukey test to run this post hoc analysis. Once again, I have equal sample size. Each group had 10 participants, so I'm able to use the Tukey test. Previously, when we were calculating the means in our data set, we found that the mean for the test scores before the course was 10. The mean for the scores immediately after taking the course was 13.5, and the mean for 6 months after the course was 12.5. So if I do all of my pairwise comparisons, this is what I get. I'm going to compare the average from before the course to immediately after the course, and I get negative 3.5 as a difference. Then I'm going to compare the scores before the course minus the scores 6 months after the course, and I get negative 2.5. And then I'm going to compare the scores immediately after the course to 6 months after, and I get a difference of 1. So using the Tukey formula, we need to calculate a critical value against which we're going to compare all of the mean differences that we've just calculated. Once again, the formula says that our critical value is equal to the Q value multiplied by mean squared within divided by the n in each group. So we first need to identify degrees of freedom within, mean squared within, k, the number of groups, and the number of people in each group. According to our source table, we know that degrees of freedom within are 18, mean squared within is 3.20, the number of groups we have are 3, and the number of people in each group is 10. So now with this information, we're going to go back to our Q table and we're going to find our critical Q value. So we know that to find the Q value, we need K, which is 3, and degrees of freedom within, which is 18. If we look at where those numbers intersect, we can see that the critical Q value is going to be 3.61. So 3.61 is the number that we're going to plug in place of Q in the formula. So if we simplify that, we have 3.61 multiplied by the square root of mean squared within, which is 3.20, divided by n in each group, which is 10. 3.61 multiplied by 0.57 gives us a critical value of 2.04. 2.04 is our critical value for the post hoc analysis. We are going to compare each mean difference to this number. So let's see what happens. These are the pairwise comparisons that we've made, and this is the critical value against which we're comparing it. Is the absolute value of 3.5 greater than or less than 2.04? Looks like it's greater than, so we can conclude that there were significant differences in test scores before taking the magic course and immediately after taking the magic course. Moving on to the next line, absolute value of 2.5, is that greater than or less than our critical value of 2.4? 2.5 looks larger by a hair than our critical value, so once again, we can identify that there are significant differences in magic scores before the course and 6 months after the course. And last but not least, if we compare the absolute value of 1 to the absolute value of 2.04, in this case, we can see that it is in fact smaller, so we conclude that there are no differences in test scores for students who took the test immediately after the course and 6 months after the course. So if we put this into a big juicy conclusion, we could say that experience in a magic course had a significant effect on the students' magic test scores when comparing their performance before the course, immediately after the course, and 6 months after the course. F, degrees of freedom 2, 18, equals our F computed value 10.16, P less than 0.05. There were significant differences in scores between those who took the magic test before the course and immediately after, as well as between those who took the test before the course and 6 months after the course. However, no differences were found between those who took the test immediately after the course and 6 months after the course. All right, beasties, we have survived the most complicated lecture of the entire course. I don't know about you, I'm a little brain fried, but it's all right. You can play, pause, repeat, do anything that you need to do to go at your own pace in order to review this information. As always, thank you for your attention and thank you for watching. And I really do wish to see you for a much less evil lecture right here on Once Upon a Lecture. Bye.